recording. There we go. Okay. All right. Increasing the pressure by decreasing the volume. Since the overall space is it bigger or is it smaller? Smaller. All of the particles, both the reactants and the products, are going to collide more frequently. And therefore, both forward and reverse rates are going to increase. So now this is the part where the explanation gets a little tricky, okay? The direction that has more gas molecules as reactants, will it have a greater or lesser increase? Greater increase. So whichever side has the more gas molecules as reactants is going to have a greater increase since the concentration of the gas molecules is affected more. And therefore, the system shifts. And I always find this part a little bit tricky to do without like a little thing to refer to. I'm going to have two A's on one side, and I'm going to have a B on the other side. I'm just randomly setting these. I'm making myself an example of a very simple system. Yes? Because I want to know, if I squish the system, is it going to shift towards the side, towards or away from the side with more gas molecules? Well, let's find out. Yes? So we have our equilibrium here. And both of the rates are going to increase, but the direction with more gas molecules is going to have a greater increase. So when we look at this direction increases more, and this direction, although it also increases, it increases less. And so are we shifting towards or away from the more gas molecules side? We're shifting away from the side with more gas molecules. This is the rate explanation is tricky, which is why we're gonna head on into Le Chatelier very soon, okay? But we're gonna do this again for decreasing pressure. And I've made all kinds of like horrible typos and mistakes here. So we're gonna correct those as we go as well. So decreasing pressure by, this should say increasing volume. And so that's going to be an upward arrow, not a downward arrow. If we have increased volume, the overall space is, greater or bigger. And therefore, all the particles, the reactants and the products, collide less frequently, yes. And therefore, both the forward and reverse rates decrease. The direction with more gas molecules as reactants will have a greater, and this is again where I made a boo-boo, it will have a greater decrease, so scribble that out there and make that a decrease in rate since the concentration of, forgot an of there, gas molecules is affected more. And so again, like I said, I have trouble thinking through whether this means I'm going to be shifting towards or away from my gas molecules. So I'm going to set up my really, really simple system. It doesn't matter where you put more gas molecules, but you can draw like a simple little one. I'm going to have more over here, and I'm going to have less over here. This is a super great trick. If you're doing a question and you don't know, you can set up like a simpler system for yourself. Like often, you know, you'll get something and it'll have weird concentrations or things like that. And you're like, well, what if I did that with 1 molar instead, right? What if I made this 1 molar and that like 2 molar? What would happen then? And you'd have nice and easy numbers to work with, and it can help you think through a problem. So that's a really good strategy to use, is to use a simple example. So both rates have decreased, but the side with more gas molecules has decreased more. So in fact, this one's going to be like tiny going forward, yes. And it's going to be a bit smaller, but not as small going backward. Okay, so we have, therefore the system is going to be shifting to the left towards the side with more gas molecules. Yes? Oh, if you have both the same, there's going to be no shift. You will have, both rates are going to, like, let's say we squished it, so we increased pressure. Both rates will go up, but they will go up by exactly the same amount. So the arrows will be the same size, so there will be no shifting involved. Okay, so what's going to happen with a rate diagram then? If we had a rate diagram for that, you would see your forward rate and your reverse rate. And then if we decrease the volume, increasing the pressure, both rates are going to go up, but they go up by the same amount, and therefore there's no shifting. So what happens is now those rates just stay the same, and so you don't get a curve, you just get new rates that are faster than before, but both still equal. Because they don't have to meet in the middle because they've already met. Okay. Similarly, concentration diagrams, you'll see a spike in the concentrations, but then they'll all just be flat because there's no shifting. Okay? And those will be in the practice problems, which are for homework tonight. So if there are the same number of gas molecules on each side, both rates increase equally or the same amount. So there will be no shift. Yeah, you'll still get a spike, but there will be no shift. Still a stress. Oh, in fact, I wrote that. Why am I writing it again? You will see a stress, but you will see no shift. There we go. So the stress is the spike. A spike is a vertical. Okay? Okay, so you will see a vertical line, but you will see no curve. Now you guys can let me know what you think of this way of arranging the explanations here. What I've done is I've put my sentence stems over on the left, yes? And then the end of the sentence is either here or it's over here. So you can think, wow, that was terrible. You're going to let me know if it's terrible and I'll redo it for next year. Okay, but what we're going to do right now is we're going to read these two boxes together. Don't circle this, okay, because we're going to change what we're reading in a moment, but just for reference. So if the stress was an increase in pressure by decreasing volume, and we're showing that here, we squished it, yes? And by squishing it, you can see now those particles are bashing into the container more often. Then if that is the stress, then therefore the system is going to shift to the side with Yes, fewer gas molecules to bring the pressure back down. Because what happened here is pressure went up, that was our stress. And so we want to bring the pressure back down. That's our shift takes care of that. And that's according to Le Chatelier's principle. What is Le Chatelier's principle again? Oh, that's not what I want to hear in a definition. But yes, that's the general idea. Okay? I want you to define it. So you're going to define it. You're going to start with when. When. Ooh, a system at equilibrium is stressed or subjected to a stress, but I like stressed because that's simple and short, yes? Is stressed. No, 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 no. You can think that in your head, but don't write that on the paper. Okay, so when a system at equilibrium is stressed, what is the response to a stress? A shift. And who does the shifting? The system will do what? Shift in order to remember, what were you trying to do with stress during your grade 12 year? You're trying to minimize it, yes? Procrastination does not minimize stress. Just letting you know, I've been there and done that. It totally increases your stress. I actually, by the time I was in third year university, I was actually trying to write up my lab reports before the course started during my semester changeover, because I was taking these labs where the discussion section was like anywhere from 25 to 40 pages long. Yes? I have no idea. I have no idea whatsoever, but so what, and a lot of that was like research. So if you knew someone who had taken the course before, you could find out what the labs were and you could go and do your background research and prepare that ahead of time. And I was like, I don't got no time when I'm taking 4 other courses to be doing all that background research and writing a 40-page paper every 2 weeks, right? So I did that ahead of time. That was by like 3rd and 4th year, I'd figured that out. That was what I had to do. Yes? Yep. In university, they're going to have their own way of doing it. And quite frankly, I am guessing for a lot of first year labs, they will have a fill in the blank sheet for you. Not for all of them. I know certainly my son's lab at UBC didn't have that, but it was online, so I don't know what it would have looked like in person. Do you know what I mean? So yeah, it really depends on where you go and what's happening. When I went through school, there was no fill in the blank sheet. It was all like, you write. It wasn't 40 pages. That was a biochem lab. We had a weird professor who was like insane. Anyway. Okay, so that is Le Chatelier's principle. So if the stress was an increase in pressure, then the system is going to shift to decrease the pressure. Yes? But not, oh, you know what? Pressure's a little bit of a different story. Just make it go down. Doesn't matter. Okay? It's only with concentration where it specifically ends above its starting place or below its starting place, depending on which way it's going. Pressure, it's just like trying to get back to normal. It's more we're doing a more qualitative study than quantitative. Okay? Just go with it for now. Just ask me later when we're doing actual examples. Yes? Okay. All right. Now we're going to not look at this second column anymore. Now we're going to look at, come on, there we go. This is our sentence stem here. Are we feeling like I should have put this on a separate page? Maybe. Anyway, so the stress was a decrease in pressure, so that is our stress by increasing the volume. And you can see here we have increased our volume. What's happening to our pressure? Yes, the pressure right now has decreased, but we want it to go back up. And if we want it to go back up, we have to shift to the side with more gas molecules. Yes? Yes. Okay. I always just think of it like this. If we've got, let's do our 2A in equilibrium with B. Yes? If I squish it, there's not as much space. So I'm going to shift to the side with less stuff because it takes up less space. Yes? What? It's increasing. The A is decreasing and B is increasing. If we are shifting to the right, that means if we are shifting to the right, that means we are using up 2 A's and we are making 1 B. So we're taking 2 particles and making 1 particle out of it. So we're making, like, the whole system is going to have fewer particles in it. Yeah. No, the spike is we squish the container, that's the spike. And the shift is the compensation. Hayden, yes. Yes. Hang on. Like there? Okay. And don't worry, we're going to be writing Le Chatelier's principle again in the temperature section. There's an actual specific space for it. So if you're like, okay, I missed it here, we're going to be doing it again. Okay, so if there are the same number of gas molecules on each side, will we be able to relieve a change in pressure by shifting? No, because if it's the same number on each side, it'll just be the same pressure regardless of whether you shift, so there will be no shift. Exactly, they're just more cramped, but the system can't compensate, right? So shifting will not be able to counteract the change in pressure, so there will be no shift. Where did that come from? That one. No shift. And you will see a stress, but no shift. So you will see a vertical spike, but no curve. Okie dokie. Now, can I get this thing back in here with no mirror? Probably not. I'm just going to put that down somewhere. Okay. Maybe we'll take it out so I'm not embarrassed. Okay. So that is it for 2C. We are now going to take a look at 2D. So that's the new one that you picked up today. If you did not pick it up, you'll want to go grab one, but I think most of you did. Yes, but okay, so the answer key, like for the notes part, what you're going to do is you're going to go to the lecture notes, because the lecture notes are all the filled in business. Yes? Yeah. On the right, very far right. Oh, the key to this one? There is no key yet. You will have it tomorrow. I tried to get it done today and I could not do it. It just did not happen in time. I had to get to school. Okay. Is the forward reaction endothermic or exothermic? Exothermic, because there's our heat term, so it is exothermic. Is the reverse rate reaction endothermic or exothermic? Endo. Forward and reverse rates are always the opposite of each other. If one is exo, the other must be endo. Which reaction has the higher activation energy? Yeah, the reverse, because it's endo. And what we're going to do is we're going to draw that. And if you had trouble visualizing that, I might have had trouble visualizing that. Don't hesitate. Draw yourself a little graph, right? Which is why I put this here, because we're going to have our potential energy and we're going to have our time. And if I was doing this on a test or something and thinking it through, I wouldn't even label those. I'd just be like, okay, my forward reaction is exothermic, so I need to start high, have my peak, and then finish lower. Yes? And when I do that, now I can see, I don't have to visualize this in my head. I can see that my forward EA which is my exothermic, is quite small. Whereas if I'm going from the products all the way up to the top, that's my EA for the reverse, which is the endo. So my reverse reaction has the higher activation energy. And in fact, it is always true that the which reaction has the higher EA, the endothermic, yes. But if you forget that, draw yourself a little graph, and there you go. What happens to the forward rate when the temperature is increased? If we increase the temperature, hold on. If I have things in a container, right, my reactants and my products are all in the same container. If I put a Bunsen burner underneath it, am I heating the reactants or am I heating the products? I'm heating them both, yes? So it doesn't matter. What happens to my forward rate when I increase the temperature? It increases. Has to increase. Why? My rate increases because my rate is higher. No, I'm saying no to that. A tautology is a tautology. Yes, okay. Forward rate increases because the particles have more kinetic energy. They're moving faster. Hold on, I'll get to you in a second, okay? So therefore, there's two things that happen because of that. More frequency of collisions. Okay, so there's a higher frequency of collisions. A higher percentage of collisions that are successful because they're more, the collisions are more energetic. Therefore, a higher percent of collisions have enough energy to be successful. It's quite the noise. What happens to our reverse rate? It increases as well. Why? Because the temperature increased, so the particles are moving faster, so they collide more frequently, and they collide with more energy. So a greater percentage of them have enough energy to be successful. So the reverse rate increases because same as above. Okay, and I knew that that was going to be a little tiny thing, so I didn't leave a lot of space for it. Okay, but, and this is what we're coming to, one of the rates is increased more than the other, which is what I think you were saying, yes? Yes. Actually, no, it's the endothermic. Yeah. The peak doesn't change. No. Okay, so what we're going to do is we're going to look at a little diagram here, okay? So first of all, just to refresh ourselves, what kind of energy are we talking about in this? This is kinetic. So this is a kinetic energy diagram. And on the side is the number of molecules. We have the blue line, which represents the colder sample, and the red dashed line, which represents the warmer sample. And we have an activation energy, which is right at that point right there. Okay. Now, there are two of these, so I'm going to just zoom out for a moment so you can see both at the same time. Okay. One of these is for the forward reaction, and one of them is for the reverse reaction. One is for the endothermic direction, and one is for the exothermic direction. Which of these is for the endothermic and which is for the exothermic? So first of all, which activation energy is higher? The one in the top diagram or the one in the bottom diagram? This is a higher activation energy, yes, because it's further along the curve. Yes? So this one here has the higher activation energy. In fact, let's give it a number. Let's say that this is, I don't know, 50 kilojoules per mole. Okay. Make something up. And that means that the one below it is maybe, oh, I don't know, 40 kilojoules per mole. Sure, let's say that. So this activation energy is the lower of the two. So which of these two represents the endothermic and which represents the exothermic? First one is endo because endo always has the higher activation energy. Yes, okay. So the first one is endothermic because it has the higher activation energy. And the other one is going to be the exothermic reaction because it has the lower EA. Now, if we're looking at our specific reaction, the endothermic direction is the reverse. And the exothermic direction is the forward. So right now, we are going to just focus on the reverse reaction to start with. And we're going to look at the fraction of collisions that are successful. If you wanted to illustrate on your diagram where the successful collisions were under the blue curve, where would that be? Successful collisions under the blue curve. Past the EA line, that's exactly right. So the successful collisions are going to be here. Doesn't matter. It's like a mathematical boundary, so who knows? You know what I mean? It's one of those math things. Okay. Now, I did a little approximation. You remember those triangles from that video? I approximated my triangles, and I counted, and I got 29 triangles to fill this whole thing. I feel like I might have been a little bit like over, but it's somewhere like I counted again and I got 25. It's going to be 20 something triangles, yes? So 1/29th of the collisions at the colder temperature will be successful. And if we want to change that into a percentage, we just divide. 1 divided by 29 gives us 3.5% of collisions are successful at the colder temperature. The shaded area is the successful collisions, yes. Isn't it nice that we're reviewing this because you have a final exam and now you're like, oh, I'm coming back to it again, yes? Yeah? Final, it'll be at the end of the course, January. So yeah, I'm letting you know right now that your winter break will not be like all, you know, jolly fun. There's going to be a lot of studying going on. However, you do have the advantage that you've got a semester break coming up, and that is like you're done your courses, right, for term 1, for semester 1. So that is just off. That's free and clear, and like, you know, just relax. You have winter break, and then we got like 3 weeks of classes or something like that, and then you got semester break. I think it's like the whole week. There's like I days in there and stuff like that, right? And people are going to be writing their literacy assessment. Yeah, so you're writing your literacy assessment. I don't know, literacy assessment. It's that thing that you write. I don't know. So I guess you don't have it off completely, but it is just walk in and do it, right? So it's not. I don't know how you study for something like that. So I would just walk in and do it. You don't need a language 12. Oh, no, you don't know. Fine. I mean, honestly, the numeracy exam is a literacy exam as well, as far as I could tell. Like, it was all like about how can you read the question. Anywho, let's get back to this. So we only had 3.5% of collisions which were successful at a colder temperature. At our warmer temperature, though, and now we've got our red shaded area, And this one was really easy for me to estimate. I'm like, oh, that looks like about a half. Yes? So I was like, okay, great, that's 50%. So 50% of collisions are successful at the warmer temperature. Yes? Oh, how do you know like how far it flattens out and lengthens? No, you just draw it farther out and lengthened, and the peak gets lower. And as long as you're like in the right ballpark, we're not going to get too excited. Okay? Yeah. Okay. So now what we do is we're going to say, well, how much more effective was, how much more collisions do we get at our warmer temperature? So I want to figure out how many times more collisions we're getting at the warmer temperature than at the colder temperature. So we are actually, if you take that 50% and divide by the 3.5%, you get 14 times. So there are 14 times as many successful collisions at the higher temperature. And remember, this is for our endothermic reaction. So when we had our endothermic reaction with that high activation energy, 14 times our rate changed by. Okay? Now we're going to look at our exothermic reaction, which has a lower activation energy. So we're going to, here's our successful collisions for our cold temperature. I'm not going to do as much labeling on this one because it's going to be just the same as the other. So there's our successful collisions. Do you agree with me that that looks like it could be about a quarter of the total area under the blue curve? Approximately. Can you be like, okay, let's give Ms. Spence some leeway and say, sure, close enough? Thank you. Rade looks unsure, but everyone else is giving me a thumbs up. I'm going to go with that. So if I have a quarter, that is 25% if I do that division there, okay? Now my warmer sample, again, we're totally ballparking these numbers. I thought that looked like about 2/3. Does that look like about 2/3? Okay, thank you. That was a nice, definite, immediate yes. So we went from having 25% successful to having 67% successful. Okay, so this is successful and 25% successful. So how many times did we multiply our successfulness when we went from cold to hot? Well, we take 67 and divide by 25, and we get only 2.7 times. So when we were dealing with our exothermic reaction, yes, we got more successful collisions, but we didn't get nearly the same multiplier. Yeah? If I zoom out, you can see for our endothermic reaction, we got a 14-time multiplier when we increased the temperature. Whereas with this one, we only got a 2.7-time multiplier. Now, am I ever going to make you draw these diagrams and approximate? The answer is no. Okay? No. You do not need to be able to do this. But what you do need to know is that if you change the temperature, which reaction is affected more? Endo. Boom. Yes? And that, my friends, is what we have in a box with stars on the next page. Yes? So what was all of that for? That's because if I just say changing temperature affects the rate of the endothermic reaction more, you go, well, why? I don't understand. And you feel uncomfortable with it, possibly, right? And if you still feel uncomfortable with it, that's okay. You can just memorize this. That's the nice thing, is that you can either understand it or you can memorize it. Either way is good. So this is what you need to know. This you need to know. So we increased the temperature. And remember, what did that do to our forward rate? Our forward rate increased. What did our reverse rate do? It also increased, yes. Now, we're going to look at this and we're going to say which of them increased more. Why the forward? Are we doing gases and pressure here, or are we doing temperature? We're doing temperature, and remember, temperature affects the rate of the endothermic reaction more. Who is our endothermic reaction? That would not be the forward reaction, that would be the reverse reaction. So this rate, this is our endothermic rate, speeds up more. And our reverse rate also speeds up, but not as much because it is exo. Why does it speed up more? It's because of all this blah, 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 blah. What it means is that if you look at these graphs, it proves it to you. Why does it do that? Because if you have a higher activation energy, you get a bigger multiplier on the change, on the effect that temperature has. And the endothermic reaction has the higher activation energy. Yeah? So like I said, you don't need to explain that, but you do need to know it. Yeah, exactly, exactly. So, yeah. Exactly. Okay, so which rate is faster? So the reverse rate is faster because although both rates increase, the reverse rate, the endothermic rate, yep, increases more. And this again is one of those situations where I love having those arrows, like the bigger arrow on the top and the smaller arrow on the bottom, because then if I'm answering a question like what's being made faster, products or reactants, I look at my arrows and say what's being made faster? Reactants are being made faster. And therefore the system is shifting to the, hold on, if we're making reactants faster, that means we're going this way. So that's to the left. Is shifting away from what? You can say it's shifting away from the heat term if you want to explain it in terms of Le Chatelier. Okay. And we're going to get to that in just a moment, and then we're going to take our break, and then we're going to do the lab. Okay. So we're almost done here. Okay, so our rate diagram here. Whew. And maybe we'll just do the diagrams and we'll finish the rest of it next day, okay? So our rate diagram, we have N2 plus 3H2 in equilibrium with 2 NH3 plus, and I'm just going to put kilojoules because I don't actually care how many there are, I just need to know that my heat term is on the right. And I wish Rade were here because I would ask him what we can say about the rates at the beginning, but I can't. So, what can I say about the rates when I'm starting this before I've done anything? They're at equilibrium, therefore the forward and reverse are equal. They are the same. Okay. Oh, and I can't forget to label my axes, rate and time. And our concentration, our forward rate, because we've increased the temperature right here, this is our increase in temperature, it's going to go up. Forward rate goes up. What does our reverse rate do? It also goes up. Does it go up by the same amount or does it go up by a different amount? It goes up more because that's our endothermic reaction, yes? Yes, so our endothermic reaction increases more, so we're going to see that go up, and I should have started this lower down or not made my forward increase as much, but that's okay, I'm just going to go way up there. That was our stress, both rates increase. Now what happens? They shift, and when they start shifting, it should be a curve, and the slope should be steep at the beginning, and then it becomes more and more shallow until eventually it is flat. And our reverse rate is also going to start curving with a steep slope at the beginning and getting more and more shallow until eventually it is also flat, and these two are once again equal to one another. And do you have to draw this little dot here? No, that's optional if you want to. I draw it simply so you can see, oh, that's where my shift started. Okay? Because I don't need one because it's like a point. Yes? I could have put a dot here, but it seems pretty obvious that that's where the change is. It's just because, you know, reverse rate is going up and then it continues to go up as it shifts, so it's hard to see the difference sometimes. Okay? All right, concentration diagram. We have N2 plus 3H2 in equilibrium with 2 NH3 plus our kilojoules. And does it matter? No. So I'm going to just arbitrarily, randomly, put my NH3 here, I'm going to put my N2 here, and I'm going to put my H2 here. I'm going to label my axes, concentration here, and time here. And right at this moment, right here, we are going to increase the temperature. Here's a question, and this is tricky. Think about it hard. What happens to our concentrations in the moment we change the temperature? Why? Imagine that we had a single gas. Yes? I don't even want an equilibrium right now. Yes? I just want to have a single gas, no reactants, no products, just a single gas in a container. When I heat it, that's my fire because I can't draw. What happens to the concentration? It stays the same. Yes? So, if a single gas's concentration stays the same in that instance, what's happening to the concentration of all my reactants and products in that instant? You can't, the temperature doesn't make them increase or decrease in concentration. So the concentrations stay the same. So guess what? This is one instance when you have a concentration diagram for a temperature stress. You will not see any vertical spikes because you're not changing concentration as a stress. Volume pressure, if I squash a container, is it? I don't want to talk about compensation. I want to say in that moment, as I go from bigger container to smaller container, did I change the concentration? But concentration isn't the same as moles. It is moles per liter. And so if this is 4 moles per 2 liters, right, which is 2 moles per liter, and then this is 4 moles per, what, 0.25 liters? Or no, half a liter, that looks like about a half. That's going to be 8 moles per liter. So a pressure change will change all the concentrations at once. We are actually going to talk about this tomorrow, how you can look at a concentration diagram and be like, oh, there's one spike. That was a concentration stress. I changed a concentration. Oh, all my things had a spike. That was a change in pressure volume. None of my things had a spike. That's a change in temperature. Okay, so that's why we're gonna take all of the stuff we did over this past week and we're gonna put it all together tomorrow. Okay. So no vertical spikes. But which way are we shifting? Well, remember, I increased both rates. Which rate increases more? The reverse rate increases more because it is endothermic. So, what's happening to the concentration of NH3 as we go that way? We're using up NH3, right? So NH3 is going to go down, okay? And so it's going to go down. I'm just going to draw, there we go. And then the other two are going to go up because they're being made. So we're making N2, H2. And are they going to go up by same amount or by different? Yeah, so if I wanted to label this with an X value, what would I use there for my ammonia? I would use 2X. And that means that when my nitrogen goes up, it's going to go up by X. And hydrogen is going to go up by 3x. So 1, 2, 3. And you see why I would want a ruler here, because I didn't draw a very straight line, okay? And we are going to take our break until 2 minutes before 2. 1:58. Yes. Yes. Like, hold on. How's that? More like this? Yeah. And I need to go here and here and press stop recording. Stop.